Good afternoon, everybody. Thank you for taking the time to come along and join us today. Today's presentation is going to be talking about alternatives to flash testing when performing testing within the tool hire industry. Just a brief kind of introduction. My name is Nathan Barwell. I'm one of the category managers here at Seaward, mostly responsible for manufacturing testers and our Clare range of testers within the hire industry. So let's briefly talk about what we're going to be discussing today. Well, firstly, we'll talk about why we do the flash test in the first place. What's its importance? What are we trying to achieve when performing the test? We'll discuss when it may not be appropriate to perform the test. We'll then briefly discuss the alternatives, those being 3 different tests that we can perform. We'll discuss insulation resistance. We'll give you an introduction to the test. We'll go through some video demonstrations, some considerations for when you should or shouldn't perform the test, and any limitations or safety aspects related to either of those tests. We'll then talk about protective conductor and touch current tests. Again, we'll introduce both of them. We'll give you some video demonstrations on both of those, discuss the considerations again, and any kind of limitations and safety aspects you may need to consider when performing any of the tests. We'll then finally finish off by briefly introducing you to the test equipment we have within the industry. And then we'll finish off and open the floor up where if you have any questions at all, please feel free to ask them using the tool provided. So why do we flash test? Well, ultimately we flash test to ensure customer safety when renting out our tools to our end users. The ultimate aim of the flash test is to ensure there's no failure in the insulating properties of the product. So we're performing the test to stress the insulation to ensure that there's no breakdown with the insulation that could ultimately then be the cause of either an electric shock or a potential fire hazard if left running. So some of the common causes and failure in the insulation that we will pick up when performing the test: any kind of breaks or splits in the insulation. So when we talk about breaks or splits in the insulation, what we're talking about is potentially somewhere where the live conductors can conduct to either the outer casing or to any of the earth cabling and therefore present a shock hazard. Over time, with use, particularly with products that are left out in the cold, you'll get some deterioration. The cables will become brittle. Again, they'll be kind of subsequent to crack or break. Any contamination by foreign bodies. This could be particularly prevalent when using grinders. For example, we could get a buildup of conductive material within the unit. That conductive material could create a path to the exposed metalwork on the product that could potentially cause a shock hazard. And any kind of excessive heat. Heat again potentially will warp the insulation, potentially causing it to melt, exposing internal conductors, and therefore providing a risk hazard. So ultimately, we do the flash test to ensure there's no breakdown in the insulation, and that we're ultimately keeping our customers safe. However, there are times where it may not be appropriate to perform a flash test. The flash test can only prove to a certain point. And some of the considerations we have to think about when performing these sort of tests are on screen now. So firstly, in order to test the unit properly, we have to make sure any switches are in the on position. Otherwise, we may only be testing up to the point of the switch. Now, if you consider something like a desk lamp, and if we were performing the test on a lamp, let's say the switch is halfway up the cable, the switch is in the off position. We've got no guarantee that we're testing beyond that switch. We may only be testing that short space of cable from the plug up to the switch. So we need to make sure the switch is in the on position in order to test the product fully. Now, this may not be possible with certain products. So if they have any kind of electronic switch where we physically cannot place the switch into the on position before the test, it may not be relevant to do a flash test. Again, anything with trigger, where the trigger can't be locked on, again, we may have the same kind of issues. We may find that the manufacturers recommend that we don't perform a high voltage test at all. It could be that components used with inside the product are not suitable for high voltage testing. The manufacturer ultimately remains the authority on his products. So if we are to receive kind of information not to perform such a test, then we should always go with the manufacturer's guidance. And hopefully the test that we talk about today will give you an alternative method to ensure that your customers are safe. And the third kind of instance where we may not be able to flash test is if we have something called overvoltage or overvoltage suppressants. I'm sure many of you will be familiar with surge protected extension leads. The purpose of those extension leads is that if they spot an overvoltage, they effectively short the live conductors to earth to send all of the excessive voltage away back down through the earth cable, keeping the product it's protecting nice and safe. Now, when we apply a high voltage test, like a flash test where we are testing at kind of 1,000 volts plus, that will always be seen as a potential hazard to these kind of devices. And therefore, what will happen is we'll actually initiate false failures where the thing sees it as being an overvoltage, effectively connects live to earth, and then our tester will see that as a short and fail the product. It's actually not a failure, it's the device doing what it's designed to do. So these are the three instances where you may need to consider not performing a flash test, and the subsequent test we'll talk about will offer you some additional methods of testing. It could be that you perform the flash test in conjunction with one of these, so you're doing a full and complete test on it, or you may substitute the flash test entirely for one of these tests. So according to the Higher Association of Europe's guidance on electrical safety testing, their code of practice recommends the following tests as being appropriate alternatives to the high voltage test. Firstly, we have our insulation resistance testing. We have our protective earth conductor current, or as it's more commonly known, earth leakage testing. And then we have our touch current test, or touch leakage, again, as it's commonly known. Throughout the presentation, we'll discuss which products are able to do certain tests. But let's move on and talk about the first test in the range, the insulation resistance test. So, as the name suggests, the insulation resistance test is a measurement of the quality of the insulation by means of a resistance test. The method of performing the test in terms of connections to the device under test and the use of probes is identical to that of the flash test. So everything you're familiar with in the higher industry in terms of how you make connections, which probes you use, where you place the probe, is effectively identical between a flash test and an insulation resistance test. The main difference really with this test is the voltage is lower. So you can see we're typically performing it at DC voltage. 500 volts is the more common test in order to stress the insulation under fault conditions. However, it is possible to perform the test at 250 volts on many of the devices out there on the market. Particularly the Claire products will perform the test at both 500 volts and 250 volts. The question is, why would you alter the voltage? Well, typically we want to stress it in the most stringent way possible. Hence why the flash test is kind of at 1,000 volts plus. So we'd always default to the highest. However, when I was talking before about the surge protected devices, it's typical that the operating voltage for these suppression devices kick in at around 300 volts. So therefore, performing the test at 500 volts will still trigger this kind of failure. So we should perform the test at 250 volts if we know the product has a surge protection. Again, it comes back to a statement in the code of practice about being reasonably practicable. What can you do to the product to ensure safety? In some instances, it's just not possible to perform that test as a higher voltage as we like. So we have to find an alternate method that will at least give us some confidence that the product is safe. So essentially, how does the test work? Well, we'll show you an animation shortly to show exactly what's going on during the test. But effectively, we strap the live and neutral test conductors together. We send the voltage up through the live and neutral conductors, and we then measure the return of any leakage current flowing down through either the earth cable if the product's a class 1, or via the probe if we're testing a class 2 product. What happens internally within the device is it takes the output voltage, takes the known leakage current that's flowing back into the device, and then converts the reading into a resistance reading. Now, what's important to note is when you do perform an insulation resistance test, the reading you're getting is different to any other test that you perform in the electrical safety environment, whereby the limit we normally read is what we call a ceiling level limit. So we want to be beneath the ceiling. In the instance of the insulation resistance, what we're looking for is a floor limit reading. So our pass-fail threshold, we need to be above that. And that's just due to the relationship between current and resistance. As the current increases, resistance will decrease. So because we're looking for a low current low amount of leakage current, transversely what we're also looking for is a high level of resistance. So typically the resistance we're reading will be measured up in mega ohms, millions of ohms. And as I said before, we're looking for a higher than reading when we're performing the test. So any limit that we set is typically a floor limit. So as we discussed, voltage is applied to the live and neutral cables tied together, and then any current flowing back will be detected either within the earth cable itself or within the flash probe. Typically pass limits are set and are quite simple to remember. If we're measuring a class 1 device, our limit will be 1 megohm. If we're measuring a class 2 device, our limit would be 2 meg. So nice and easy to remember. In terms of quick kind of connection diagrams, you'll see on screen here. For a class 1, as we've said, there's no need for any additional probes. Everything is measured between the internal conductors of the device we're testing. So the live and neutral are used to output the voltage, and then the earth cable is used as a measurement probe to pick up any earth leakage flowing back into the device that is then measured by the tester. With a class 2 product, as we all know, there's no earth cable. So with the lack of an earth cable, what we do is simply apply an external probe to expose metalwork. And again, those points will be exactly the same points that you might do when performing the flash test. Any current flow is then picked up, flows back into the instrument, and again is the limit is judged according to what's flowing back. So what we're going to do at this point is just take a brief pause in the presentation. We're going to demonstrate a couple of videos showing how to perform the tests. We'll use one of our testers that are used in the hire industry. And once that's finished, we'll come back and we'll discuss the other tests in the range.
Insulation testing is carried out by plugging the tested appliance into the PAT and applying a test voltage of 500 volts DC to both the live and neutral terminals of the mains plug. If the insulation is in good condition, a high insulation resistance reading is obtained, typically in the order of hundreds of mega ohms. If there is a breakdown in insulation between live parts and protective earth, a current will flow across the insulation and back to the PAT via the protective earth conductor. The measured insulation resistance is greatly reduced, indicative of an insulation fault. When testing insulation on a Class 2 appliance, the test probe is connected to any exposed metal parts. If the exposed metal parts are insulated from live parts, a high insulation resistance measurement is obtained. If there is a breakdown in insulation between live parts and any exposed metal parts, a current will flow across the insulation and back to the PAT via the test probe. The measured insulation resistance is greatly reduced, indicative of an insulation fault.
So we've seen the insulation resistance test in that little animated diagram there. We're going to see what it looks like in the real world. We're going to use this little heater and test the insulation of the heater. So we're going to turn it on, make sure it's turned on for this test, turn it up to max and plug it in. We're also going to attach the earth bond clip to check the earth continuity to make sure that it's safe to actually do the insulation resistance test. So we're going to go new test, put in any old appliance number, choose our insulation resistance test, start off with an earth bond test, make sure the earth's good. Excellent. And now moving on to the insulation resistance tests. So as it's showed in that previous little video, we're going to use live and neutral strapped together, put 500 volts across those, and measure the resistance between those and the metal parts and the earth cable. So I'm going to start this test. We're after a nice high resistance here. And you can see we've got a very high resistance, so that's a pass.
Okay, so hopefully the video's proved useful there. Let's move on and discuss the considerations for use when performing an insulation resistance test. So, as we said before, if a manufacturer recommends that a high voltage test isn't suitable, the insulation resistance test could absolutely be the solution to that. In effect, we're only really applying double the mains voltage, and certainly any product on the market should be able to withstand that level of voltage, particularly if it's being powered from a main supply. As we said, from a training point of view, the procedure is identical to that of flash testing, so it's not too difficult to train your operators in performing these tests. Considerations on a class 1 item: you should only perform this test once you've performed an earth bond test. It's important that we know the earth bond is connected and the earth cable is doing its job before performing any class 1 leakage test, whether that's a flash test, an insulation resistance, or the protective earth conductor current test that we speak about a little bit later. Now, why is it important? Well, if the earth cable wasn't there and we hadn't performed an earth test on it, we would never have a return path for the leakage current. So it's important to note that make sure you do your earth bond test prior to doing any level of insulation resistance or any test on the insulation at all, because the test is relying on the earth cable to be there in order to get a good measurement. And as we previously mentioned, this test is suitable for overvoltage suppression devices. So again, surge protected extension leads, if it's performed at 250 volts. But what about kind of limitations and any safety considerations? Well, as we said, whilst it's useful in circumstances where the manufacturer may not apply the high voltage, it does have limitations. It's not suitable for testing at 500 volts where surge protection is prevalent. Again, we're going to fall into the same trap of getting potential false failures. And it's also not recommended in the event that you cannot engage a mains voltage switch. So, for example, a contact switch on a concrete mixer, if you've got that sort of environment, then a dead test, i.e. a flash or insulation resistance, may not be suitable at all. In such cases, it's probably more suitable to perform the other tests that we're going to talk about today, the mains powered tests, because they're done while the unit is operational and powered on. So we'll discuss these as we move on now. So as we've said, for safe use, for limitations, if it's got overvoltage suppression, then we may not be able to do this test. And again, if we cannot physically turn the unit on, then again, we may not be able to perform the test. So if your device that you're testing has any of those characteristics, it may not be possible to get a good test, and you should consider performing a more suitable test, either in accordance with, so a flash test or an insulation resistance, followed by one of the mains tests we're about to discuss, or just the mains tests themselves. So let's talk now about the protective earth conductor current, or as many of you know it, an earth leakage test. As the name suggests, the test is used to determine any leakage current that's flowing away from the insulation and into the earth cable. This flow may be coming from poorly insulated devices, flowing onto the chassis of the device, and then into the protective path, i.e. the earth cable. As we hinted, when you're discussing insulation tests, it may be more applicable to perform the test whilst the unit is in operation. So this will generally mean that in the hire industry, we're either performing tests at 110 volt or 240 volt, dependent on the device and the test operating voltage. When we're attempting to decide what's a good or correct pass or fail limit for the product, there's a few questions we kind of need to understand and ask ourselves. Typically, it's to do with whether the device is handheld, is it portable, is it a stationary piece of equipment, or is it a heating element? So once you've kind of dealt with those kind of questions, you can really decide what the correct pass limit is. And you'll see here, we have, for anything that's class 1, that's a heating appliance, so any of your kind of red rads or anything like that you have, we're typically looking for a pass limit of 0.75 milliamps or 0.75 milliamps per kilowatt. So you simply multiply 0.75 by however many kilowatts the heater is, and that will define your pass limit. Now, the Code of Practice does recommend a maximum of 5 milliamps. So, you know, if your calculation goes higher than that, we should still apply a maximum limit of 5 milliamps. Anything portable or handheld, so anything that's either designed to be in operation whilst you're holding it, or anything that's very easy to move around, would have a 0.75 milliamps limit. Now, when we're talking about handheld here, we're not talking about double insulated handheld equipment. This is anything that's earthed. Anything else, any other kind of class 1 equipment would have a limit of 3.5 milliamps. So that, again, generally would be something that is either what we call transportable or stationary, something that's designed to be used in one place without moving around. It may have handles to transport it whilst not in operation, but it's typically designed that whilst it's in operation, it's kind of stood in one place. So when we're talking about leakage tests or protective earth conductor currents, there's two different methods that a piece of test equipment can employ to perform the test. There's either what we call the direct measurement method, or there's what we call the differential method. Now, typically this won't really matter to you guys doing the test. This is more to do with how the tester performs the test, and it does it in one of two ways. There's either what we call the direct measurement. So the direct measurement requires the test equipment to have an ammeter capable of reading the current flow in the earth path of the device. So very, very simply, what this does, you power the equipment on, there's a measuring device that simply measures any current flow flowing back into the test equipment via the earth cable. So to ensure a good reading in this case, it's essential the unit under test is disconnected from any sources of grounding. So we've only got the one path flowing back into it. So if, for example, you had a device and it had an external earth connection, it's important that earth connection is disconnected. So the only path back into the instrument is via the protective conductor, i.e. the earth cable. So what this does, eliminates any secondary paths. Now those secondary paths could be flowing away from the device and therefore not being picked up by the tester, which could give you an inaccurate reading. So as I said, the direct method, we simply power the equipment up, live and neutral are flowing through the device is active, and the test equipment is measuring any current that is flowing back into the instrument via the earth cable. The alternate method for this is what we call the differential method. As the name suggests, the differential method measures the differences in the current flowing in both the live and neutral conductors. So in this case, it does it slightly different. It measures the the current flowing up through the live conductor and measures the current flowing back via the neutral conductor. Now, in an ideal world where there's no leakage existing, the current flow would be zero, and therefore what we would have is a balanced supply, i.e. all the current flowing up through the neutral is flowing through the device, and all of that current is flowing back via the neutral. So it flows up through the live, through the device, back down through the neutral, and there's no difference in the current. Where we do have leakage, then we may have a difference in the currents flowing in the two conductors, and that is essentially how the differential method works. It just simply understands the difference between the current flowing in the live and the neutral conductors. The advantage of the differential method is that the current, or any kind of external paths to earth, do not have to be eradicated in this case. So if there was a path on a product that led to a pipe, and that pipe flowed to earth, we wouldn't need to disconnect that, because now we're just seeing exactly what the difference is between the two between the two conductors. So any leakage, wherever it's flowing away from the instrument, will be picked up via the differential method. As I say, it's not really something to worry about. For those of you that want to know, if you have a B255, that employs the direct measurement path. If you have a SafeCheck 8, that employs the differential method. So let's have a quick look at the diagram. In this case, we've used the B255, but again, you can see that there's no test probe required for this test. All the measurements, as per a Class 1 insulation or a Class 1 flash test, are all performed between the internal conductors, and it's the earth cable that acts as a return for any stray leakage current. Okay, at this point, we're just going to pause, and we're going to show you again a couple of videos and some animations defining exactly what's happening during the test.
To measure a protective conductor current, the appliance is plugged into the PAT. When the appliance is energized, current will flow from the main supply to the appliance in the live conductor, indicated via the brown arrow, and then return to the supply via the neutral conductor. If there is good insulation between live parts and protective earth, the live and neutral currents are equal, i.e., all of the current entering the appliance in the live conductor returns to the supply in the neutral. If there is a fault with the insulation, some of the current flowing in the live conductor will return to the supply via the protective earth. The PAT will detect this imbalance in the live and neutral currents and display the result.
So this time, using the B255, we're going to do an earth leakage test. Again, we're going to switch onto the earth test first. We've got our earth probe attached, make sure everything's turned on, all plugged in. We're going to run the earth test. We're in the good white pass area there, so we've got a pass on the earth, so we're safe to move on to the powered test. Turn it all the way around to earth leakage. Now this time it is going to power up the equipment, so just be aware of that. I mean, this is a heater that I'm using, so when I power this up, it is going to get hot. Be aware that whatever you've got plugged in is going to heat up. So this time I'm going to hit load test. So I'm now powering up this heater. I can feel it getting warmer. And we're looking for this leakage. This leakage at the bottom is what we're after. And so you can see that we're getting a very low milliamp leakage here, so that's fantastic.
Okay, so we've had a look now at the protective earth conductor current test. Let's have a quick look at the touch leakage test. So, similar to the protective earth conductor current, we're performing the test at operating voltage, so typically 240 or 110 volt operation. The test again is conducted while the equipment under test is in operation. Now, we call this a touch current test because essentially what we're doing is we're simulating the current that would flow through a human if they were to touch the device whilst it's in operation. So what we do is we apply a test clip or probe to the device to simulate a human touch. Essentially, we're putting a clip on the product to effectively act like a human. So if we were to touch that part of the product under test, what current would flow through our hand, i.e. the clip, and is that current high enough to cause us an issue? In the case of a touch current test, it's pretty much performed only on double insulated or class 2 products where there isn't an earth. So therefore the clip is also acting as the return back to the device. Now very similarly, like us, if we touch the class 2 product, there was no earth there for protection and the live cable was in contact with the outer casing, we would act as the return to ground, therefore we put ourselves in shock hazard. So that's why we perform the test, to ensure that there's no path that we could touch that would cause us any kind of injury. So as we said, during the test, the current flows back into the device via the test clip. Now what we do when it flows through that test clip is we also divert that current through what we call a body model. Now, for those of you that have been on any of our previous webinars, we talk about the human resistance of the human body. We have a rough resistance of somewhere in the region of 1500 to 2000 ohms. So essentially what we do is we divert this current through the body model, which is essentially a 2000 ohm resistor, and this gives us a realistic value for what current we would be exposed to if there's an issue with the product under test. Now, for this reason, because we're talking about currents flowing through the body, we have a very strict pass-fail threshold on this test. And in this case, it doesn't matter about the type of equipment we're testing. So it doesn't matter whether it's handheld, portable, stationary. The pass limit for a touch leakage device is fixed across all devices, and that's at 0.25 milliamps. So any current flowing greater than 0.25 milliamps should be deemed a failure when performing a touch current test. So again, much like before, here's a typical touch current connection diagram. Now, we've shown the B255 because there is an important point to note with regards to test clip placement when performing the test. Now, in order to perform the touch current test, we need to provide a return back into the instrument. For those of you that have a SafeCheck 8, the return path is simply the crocodile clip, the black crocodile clip that's supplied on the device. That's plugged into the back of the unit, and everything's fine. With the B255, we have to move the probe or the clip around the bar. So we're going to be using on a B255 the same green cabled clip that we use for the earth test. The difference is we have to take the clip or the probe from the back of the unit, so where the plug hits the back of the B255, we have to remove it from that point, and we simply move it to the front on the output box. You'll see there's a green 4mm socket. So we need to put the clip into that 4mm socket and then onto any exposed metalwork on the device that we're testing. And it's important to do that to ensure you get the measurement through the body model, and therefore we get a representative test. So at this stage, we're just again going to pause the presentation. We're going to show you a couple of videos and some animations of a touch current test being performed, and then we'll come back and we'll talk again about the considerations for each of the different types of tests.
The touch current test is carried out by connecting the PAT to the appliance and the test probe to any exposed metal parts. If there is fault with the insulation, some of the current flowing in the live conductor will return to the supply via the test probe.
To do a touch leakage with the B255, we need to use the earth bond clip, but this time we need to unplug it from the back of the B255. Get that cable, we need to put it into this little slot here. So this little slot has our 2 kiloohm resistor in it. It's going to do the touch leakage measurement. I'm going to then clip my clip onto part of the exposed metal that's not going to move when I start this test, because remember, the touch leakage test is going to power up the equipment. So the moving parts of the equipment will start to move as soon as I press go. I'm going to go onto earth leakage, which is this one here, and then I'm going to hit the load button, and we're going to power up the equipment and get a touch leakage measurement on this bottom scale here. So you can see we're getting a very little reading there, showing the touch leakage measurement.
Okay, so we're going to move on and talk about the considerations for use, any limitations and reasons for safe use. Now, we have bundled both the considerations and the limitations for both the touch current and the protective earth conductor current, purely because the limitations are one and the same. So it is a highly versatile test. Essentially, we're only performing the test at normal operating voltage, so it's suitable for any of our 110 240 volt products. It's particularly suited to applications where the manufacturer does recommend that repeated high voltage testing could cause wear and tear in the device and ultimately make it less safe. It's absolutely suitable for suppression devices, because again we're performing the test at mains voltage, so 110 or 240 volt, so we're not going to trigger any of the surge protection within these sort of devices. It's completely suitable for devices with contactor type switches, the caveat being that we have to switch them on. So we apply power, we press the main switch, the unit then powers up. We then can be sure that the entire circuit is engaged, and therefore any leakage will be representative of the product under test whilst it's operational. For the protective earth conductor current test, very similar to previous guidance about the insulation resistance test. You should only perform this test on a class 1 item after you've performed the earth bond test. Again, just to repeat why, it's to ensure that the earth cable, which is part of the measuring circuit, is in place and doing its job. If it isn't there, we could get a reading of 0 leakage because there's nothing for that current to flow down back into the device to give us a good reading. Now, good practice when performing either a protective earth conductor current test or a touch current test is that we always ensure any setting that drives the device is set to its maximum. So if you have any kind of dials for speed settings, if you have any multi-switches for things like elements, so if your radiators have kind of multiple switches to switch on all the elements, we'd recommend certainly, if you can, switching them all on so that you're really driving the device at its max, and therefore any leakage would be at its maximum too. So what about safe usage of these types of tests? Well, again, both for the touch current and the protective earth conductor current tests, it's worth noting that the unit will become live. So during these tests, it will do what it's designed to do. So with that in mind, if there are any cutting, drilling, or any other kind of sharps that are activated when the unit's operational, we would always recommend that they are removed prior to testing and removed by a suitably skilled person that understands exactly how to remove these blades or cutting devices safely. What we don't want to happen is the device to start up, the cutting blade is exposed, and therefore we present a potential risk to our test operators. When the test starts, again, it could start quite suddenly. So anything with a motor-driven kind of equipment, grinders example I've seen, where you start the test off and these things start up instantly, they could start jumping around on the workstation. So it's generally recommended that if you can, you suitably restrain the device. Something like a vise or some straps may be required just to hold the device down nice and safely so it doesn't hop around when you start the test off. And then finally, always remember again, if it's a heating piece of kit that you're testing, it's going to get hot, and it may be hot after the test is finished. So you need to consider kind of picking it up, moving it. The certain parts of the device under test may still be hot once it's finished. Obviously, if it's hot, never test that whilst it's pointing at the operator, and obviously remove anything flammable from the test area, just so you don't pose any risk that the heat can catch fire to anything that it shouldn't. When you're performing the touch leakage test, you must pay attention to where you're going to put the clip. Obviously, certain elements, certain metal parts will move. What we don't want to do is place the clip somewhere that potentially then could be damaged, therefore causing damage to your equipment, or thrown off, potentially causing harm to your operators. The clips do have kind of teeth on them. We wouldn't want those to hit the operators potentially in the eye or anywhere else that could cause injury. So always kind of ensure that wherever you put the clip, it's not being placed onto a moving part that could cause harm to anyone if it flipped off. So hopefully that's given you a good indication about the alternatives to flash testing. I just want to quickly kind of introduce you to our test range and talk about what features they do have. And then we'll throw the stage open to you. If you have any questions, please feel free to fire them through. So essentially our Seaward range of equipment, we have two 2 products that are absolutely dedicated and manufactured in accordance with guidance for the hire industry. So we have our SafeCheck 8 instrument. This is the more modern of the 2 instruments. It performs tests sequentially, so you can pre-configure test sequences, and that test sequence will run through a list of tests with all the limits, all the times defined by you, and makes things nice and easy for the operators. It has memory, so it can store results. You can output them to a PC, so you can have a digital record of any of the tests that you've performed. It can also work with things like label printers, so you can instantly pass or print out a label that can go on the device as soon as it's finished testing. So if anyone was to query it, it's got a label on with a date of test. You can even print out the measured values on that if required. So if you wanted to assign a mini certificate onto your product after it's been tested, you can do that with the SafeCheck 8 solution. In terms of test capabilities, it will perform the earth bond test, the flash test, the insulation resistance, the touch and protective conductor current test that we spoke about today, along with load testing. Our other alternative, the workhorse, the industry standard as we like to call it, the B255, very simple, very well-known instrument in the hire industry. Single function test selected by a very big, easy to use dial, very easy to use. In this case, it performs earth testing, flash testing, protective conductor current, and load testing and touch leakage testing. It doesn't perform the insulation resistance test, but you still have the protective conductor current and the touch current test as alternatives where you may not perform a flash test. So that brings us to the end of the presentation today. I hope you've all found it useful. As we said, if you do have any questions regarding any of the content today or any general questions regarding testing in the industry, we're going to hang around for a little while now. There is a feature on the webinar software that you've installed. It will give you the ability to ask questions. Please feel free to fire those questions to us now. We'll hang around and we'll answer them via text or from the microphone where we need to. Alternatively, if you do want to get in touch, please feel free to contact us at sales@seaward.com. Again, if you have any questions and you want us to send them via email, please feel free and we'll come back to you directly. We'd also like suggestions from you regarding future content. If there's anything that you guys would like us to discuss that would help you, please feel free to send those in, suggestions. If there's any content for any of these webinars, how-to tests, for example, if you want to know how to test particular products, please, any suggestions you have, feel free to fire them through and we're happy to look at those and maybe include them in future content. But outside of that, I'd like to thank you all again for coming. I'll end the audio portion of this now and we'll move over to any questions that you may have. Thanks again and enjoy the rest of your day.